Well, yeah, I'm not blinded. I'm Ola Nilsen, University of Oslo, working with ALD for some time and also MLD for some time. And it's good to see you students. Can all the students raise their hands now? Can all the students raise their hands now? Great! Can you hear me on the backs there? Yes, you can hear me. When you can't hear me any longer, go like this. Great, thanks. I'm going to talk about the transition from ALD to MLD. And then we're going to go a bit into organic chemistry. So all of you students who are skilled in organic chemistry, can you raise your hands now? Great! We have a community of organic chemists here, and they have so much to learn as inorganic chemists. Because what we basically are going to do is to exploit that type of chemistry more than what we used to. I'm going to talk about, well, basically starting on the polymer work, and then let's follow in this line here. We'll see how far we get, hopefully to the end. But before we go much deeper into it, then this is my version of the ALD. So Christoph, very nice of you for the introduction here, so I'll be brief. It's a cyclic manner, and we're exploiting the chemistries that are on the surface. This is the traditional aluminium oxide by trimetal aluminium and water. And the fact that you then saturate the surface, here you even see some unreacted hydroxyl groups on the side. This perfect reaction here, if you dig into it, you'll find that it's not really that perfect. So, but then it all is a question of how picky are you? You will run into a lot of chemistries that are not perfect. Almost all are not perfect. But then again, you are going to make a material, hopefully doing something. And as long as it does the work, who cares? So that is one mindset throughout the whole principle. And there's another technique here which we're going to dwell on quite a lot during here, and that's the quartz crystal microbalance. Those of you who are skilled in physical vapor deposition, any of you students who have worked with physical vapor deposition before? Yeah. Here we have a group as well. You have clearly worked with this quartz crystal microbalance method for calibrating the growth rates. We use it in ALD as well, but here they react on the surface, and you measure the mass of each reaction step. So what you see here is actually the mass of one molecular or atomic layer. The readout is in Hertz. The relation between Hertz and mass is linear. You can get it through the Sauber equation, but we warn, don't just go directly with the Sauber equation, because that relies on that you have a complete control of the surface area of the quartz crystal. It starts off rough. You are going to make a film which typically might be less rough or more rough, so we are going to change the effective surface area during growth. For campaigns of run, you will see this, so when you rely on this as a technique, use an internal standard. So that's great. Then the technique itself, even though it may be called ALD or MLD, have been used for depositing numerous different materials. Inorganic compounds is the, well, archetype, the one that we like to talk about, because it's a compound. You get a clear cation, you get a clear anion, and you combine them to make a reaction. It is always easier to oxidize than to reduce. That we see with our building structures as well. They clearly deteriorate through oxidation. Very few buildings that fall down due to reduction. So, therefore, metals is a bit more cumbersome. There are new chemistries coming on that makes deposition of metals even more interesting in the future. So, but I'm not going to focus on these today. I'm going to focus on the group over here, the hybrid and the organic. And let's start with the organic, the polymer itself. Because that is the untraditional, not really untraditional, but it's, yeah, but when you make polymer structures as a bulk polymer, you do it in a solution, you use a catalyst, you use a solvent that can take up your protons and keep it on the storage shelf and then use them. Here, through the gas phase, you don't have the solvent, you don't have the catalyst. You can play with temperature. That's the thing you can do. So, what was the first demonstration of this was in 91, where they grew a polyimide through the reaction of an anhydride and a amine, a diamine. When you hear this anhydride, then that's a checkpoint. Yes, interesting chemical. Because an anhydride likes to seek something that could be water. So this anhydride could react with something that resembles the protonation of the water, here in terms of the amines. And then you can form a polymer. For growth of this material here, they used more or less similar to the PVD type of system, where they expose the surface to the different precursor. So this DNB, diamino nitrobenzene molecule here, it was then deposited onto the surface where the substrate was kept at 50 degrees. And you have a nice saturation curve where you don't get more on the surface even though you expose it, and it remains. For the same temperature on the substrate, if you then deposited this material, you have a quick step and then a slow step. This is something that I anticipate that you're going to see for most of your systems in the future as well. Some chemistries go in there. There are numerous reasons why. This here is claimed to be some physisorption. Okay, you could get rid of that additional physisorption step by increasing the temperature up to 80 degrees. So then it looks very nicely. The challenge is then what happens to this DNB when you go to 80 degrees is that even at 65 degrees, you can deposit it, but as soon as you close the shutter, you lose it. So in order to grow this polymer here, they have to vary the temperature of the substrate according to while they deposited the different material. Okay, that's a bit more cumbersome to have a fluctuation in temperature during deposition, but it is possible. It isn't impossible. But by flipping this chemistry here over to this type of diamine, they could do it all at one temperature and get these nice saturation steps. You will notice that the saturation times are somewhat long. They are somewhat long in numerous reasons. One thing, polymeric reactions without catalyst, without solvent that maintains the protons, is not really in your favor from the beginning on. But also, here they use a fairly low temperature on the source, much lower than I would anticipate. And ergo, the flux of the precursor to the substrate is fairly low. So this is possible to speed up. It is. But that means also that you have a very window. You have actually a large window that you can play with these organic molecules versus the way you do it at a very low flux to your substrate, inefficient deposition, but really nice for science. Or whether you like to, if you need to optimize the process for production, then perhaps not your precursor is the best. So there's always these benefits and drawbacks. Okay. You could stretch this further. You can make polyamides, this type of functionality, where you then use this acyl chloride and a diamine. Relatively nice saturation curves. I say relatively. It's not flat. It's not completely nice flat, but it's durable. So, and you can make nice materials over here as well. This process here was not monitored by the quartz crystal microbalance, it was monitored through FDIR. And if you have the possibilities of having an in-situ FDIR, go ahead. You can follow the chemistry, you can follow the evolution of these peaks, and you saw that the growth rate, it diminished when you increase the temperature. So the growth rate versus temperature drops. This is at 157 degrees, and this is then at 62 degrees. So we have a general drop in temperature for higher, a drop in growth rate for higher temperatures. Which I think we're going to see again. You can make polyamides by using terephthalic aldehyde and the diamides. And you get this type of linker bonds. In this work that I refer to here, they made a large effort in using polarized iolite to check whether the structures were vertical or horizontal. In later works that I played with, they played with grouping this with all the type of molecules in between and treated this as quantum dots. A ring structure is in fact a very small quantum dot. So we had possibilities to play with other types of nanostructures that the organic chemistry can provide us. It's a bit scary for an inorganic chemistry to actually see being told that this is a quantum dot, but of course it is. Polyurea, even so. Then the isocyanides and the diamides, they are frequently reoccurring here. In this work, they philosophized kind of nicely on how your polymer, not standing vertically but standing at a certain angle. That's a bit of a difficult to actually pinpoint and prove how they are located in the structure, but it's a nice philosophy. Or you could say that your film is not completely dense throughout when you grow. Again, the growth rate diminishes with a higher temperature. So for the polymer structure, it seems like they work best at lower temperature when you can have your precursors at a long time on the surface. So you have an effective high concentration of this, so you get time to react. Thyrea. Okay, if you can do something with an oxygen group, then you typically can also try it with a sulfur group on the end. They're a bit more smelly, but they do show the similar type of chemistry. But still, it's a fairly long dose times that you need here. We're talking about 1,200 seconds to saturation, because you go low in temperature. But you do get a linear growth. A linear growth isn't proof of ALD, because you can get linear growth with just pure CVD as well, as long as the CVD process is stable. But if it works and gives you the product that you want to characterize in the end, then it's all about what are you actually seeking. You can combine all of this and put one type of polymer and then with another polymer, and then combine the different polymers and make copolymers. So where am I getting with this? This is more or less as a nice toolbox that you can add on to the system that you're already growing. If you have challenges with the biofunctionalities that we're going to see later on, you can't split your reaction on and use this polymeric structure. So this is one basis for the pure polymeric structure. But then again, we have the possibilities to combine the organic and inorganic structure. You can even do it in a multi-layered fashion. That's another version of this hybrid material. Hybrid just means that you combine two things. So if you combine an organic and an inorganic, even on two films relatively thick, you can't claim that that is a hybrid material. And there's a lot of effects you can get from that as well. But what I'd like to do now is to combine it even more densely. So I want to focus on that and go through what happens if you grow aluminium oxide. Aluminium oxide, you take trimetal aluminium and water. And we've done a lot of that as well. In your one precursor here is water. Now the question is, what else looks like water? When you design your system, you know that this works. Can you then find something that is water, but not water. One of the first things that we tried was the hydroquinone. If you just remove this part in the middle here, you're left with water. So the question is, does it react like water? And in essence, it does. It gives you a structure resembling this. It is amorphous, which the majority of the compounds are going to be. Therefore, they're going to be a bit difficult to pinpoint exactly what you have. But you can still characterize them. And its growth is described here. So this was actually the first system grown in by this method here. Works nice. And then you can exploit it further, because you can find out this. Okay, so the dialcohols, that's water. By the carboxylic acids, if you leave this, that's also water. And this here is just another version of ammonia. You know that works. You can combine it, so you get mixed types of chemistry. And you can also consider this as a loose base, see if you can play with it. So suddenly, if you expand into this direction, you have a much wider plethora of chemistries for the anion side. So you can build on that. Great. Let's go a bit into the chemistries here. So we have here the alcohols. The alcohols was the first that was explored. They're a natural starting point because they are so close to water that, yeah, they're there. Some of the first nice description of them is, well, using ethylene glycol. This is one of the simpler versions. And there you got the term the alcone, or the metal cone material. Its origin is based on the silicone, which also looks like an alkoxide based on silicon. There you have a silicon-oxygen-silicon network structure. The question is whether you got the same network structure in here, but hey, you need a name. So it fits. Okay. You can imagine this structure here, and here shows some of the plethora that you will have. Because aluminium oxide, when you grow aluminium oxide, pure aluminium oxide, it is amorphous because it has too much freedom with respect to double bonding or single bonding on the surface. And again, if you add on more possibilities, more complexion here on the anion side, then of course it continues in an amorphous manner. But also during growth, you see some discrepancies. So what you've done here is that you monitor the quartz crystal microbalance in the initial states and during growth later on. What you see is that for the ethylene glycol, it seems fairly similar, but the TMA gets these spikes. So the question is, what is the origin of the spikes? And we will get back to that later, but just notice it and keep it fresh in mind. But from a single point of view, you have fairly nice saturation growth and can use it on that point. They do react when taken out. They are not stable. And you do have the possibility to get double reactions on the surface. You have a drop in growth with an increase in temperature again. And there are some hints that you absorb and you don't get complete reaction of the TMA, particularly at lower temperature. So if you then take them out and let it react, something happens to your film. This here drops in thickness, and from FDIR they claim to see these dehydration reactions, but it's not consistent. Okay, this is for the short alcohol. If you then go for the bit longer alcohol, then you will see that, yes, the alcohol itself seems to saturate nicely, but you need very long exposures to saturate TMA, and then you need very long purges to get it out again. So the question is, what happens to the TMA? And the more voluminous your ligand becomes, the more likely you are to enter into such issues. We will cover that again later. But again, mention that the ligand with a bifunctionality, it can bend. And if it bends and reacts all with the surface, then what's the next step of reaction? So you more or less kill it off. Hopefully not everything does that. Or perhaps you could exploit it. Or perhaps you could stiffen up the backbone so that it doesn't bend. So one way to stiffen it up is by adding these double bonds. We know that they are much more rigid structures. And that's also why I started off with a hydroquinone for the very first case as well, because we anticipated this to happen. And if you then go with the aromatic structures, the hydroquinone and fluoroglycinol as a rigid, and you use the trimetal aluminium anion approach, you can get quartz crystal features like this. For the double OH groups, you have a nice, fairly nice saturation. You don't lose too much of your anion, but for a triple OH, it's obvious that you get a much higher, physisorption, but still it seems to saturate. What I find most interesting in this is if you normalize, not normalize, but if you actually carefully check how much TMA do I react, then it's the same amount of TMA that goes into your film for both of these, even though you have 3 OH groups here and 2 OH groups there. So it seems like that is just controlled by the area available, but the number of these ligands is defined by something else. The ideal reaction scheme is plotted on here, and obviously there is something wrong with the ideal reaction schemes, because these values, how many of these that you react per pulse, it's a bit detailed to go into it, should be between 1 and 3, and they are not. So it's not quite fairly easy to describe. This alcohol base also reacts subsequently. This is the thickness as deposited when you then run to your reflectometer. Perhaps you haven't run fast enough, because over time the fluoroglycinol version increases in thickness, whereas the hydroquinone decreases in thickness over time. So there's not a complete version there. But what you notice as well, they are fairly stable with deposition temperature, and you can deposit a stable material up to kind of nice high temperatures without the anions decomposing. When you deposit on the quartz crystal microbalance, the first experiment is going to be on pure gold. Pure gold has a different chemistry than your aluminium oxide if you nucleate that, and you do see the same deviation in the beginning. But if you start off here with a nice aluminium oxide, you don't see this limitation in the beginning. So they are also affected by the same thing there. Okay, this material turned out to also have diffraction peaks. And the diffraction peaks for the as deposited and air treated was a bit different. And they were a bit different if you treated them as well. If you did rocking curve analysis on this, we found out that they had the same intensity overall. So this is not an orientation effect. We've not been able to actually decipher why they have the diffraction peaks they have. It's not due to the pure ligands themselves, and there's so few to look for. Okay. You can play with the chemistry even further. One of those that I found rather interesting is if you use this diacetylene, this ligand here. It has a very rigid structure, and you can grow them, for instance, with diethyl zinc, but if you expose this to UV, you can get a cross-linking in plane afterwards. And suddenly you can get a different sort of homogeneity and conductivity in the film. Saturates nicely, in principle. So you can consider acting that. You can try to get away with a double reaction by using a heterofunctionality as well. There's a glycidol. You could claim that it is a heterofunctionality, but in principle this OH here can also be reactive, so it can double react. But it's one step towards it, so that you form this diol more or less in situ on the film itself. Again, you have a growth rate that drops with higher temperature, and you have an inhibition in the growth in the beginning, and you also see these spiked features on the TMA. not for the anion in this case. Look at this feature here. You have a lag in the beginning and then it takes off. Try to remember this graph here. You could go another approach. You could, for instance, just say that, okay, now I want to combine what we learned for the polymer growth itself with the MLE growth and going for an ABC type of version. Because here, if you start off with a carboxylic acid, you go on with the your trimetal aluminium, and then this heterofunctionality here, you hope and believe that the OH group will be more prone to reacting with aluminium than the amine. It's not always like that. You can get nice reactions to the diamine and the trimetal aluminium as well, but you have a huge difficulty in characterizing the film later on because it's going to react instantaneously when you take it off of the reactor. Whereas the one with the alcohol is going to also react, but not instantaneously. So we have tried that as well. Then you get the amine reaction, and then you can go with the anhydride that reacts with the amine, and you're back again with the carboxylic group. So here you can put in this functionality. What I find more interesting with this one is that here you get the possibility to drive a charge in a film. Because the charges up here are going to be different than here, so in principle what you're doing is that you're building in a polarity in the film. Perhaps that could be exploded. So, the growth of this material in the 3 version, you see that again the TMA spikes, and the other one not so much. It has an inhibition challenge in the beginning. So just keep in mind that that can happen. You can also build chemistries through self-assembled monolayers. Self-assembled monolayers is this established technique in order to control wetting of the surfaces. Just expose your film with desalinization, but if you do it with a double bond in the end, then you can do what we do with when you grow the inorganic materials, go on with the ozone and convert the double bonds to this. It's a common thought that ozone just burns every organic stuff you have in the film. Not so. There's a lot of organics which is resistant to ozone. It depends on the time frame, yes. But the double bonds are attacked much more quickly, and here you can reactivate the surface for another type of growth. This also works with the aromatic ring structures that you have, so you can do that. They tested this for controlling the wetting phase, and in this case they also monitor more or less by XPS the amount of oxygen and amount of carbon. So numerous ways you can monitor the growth itself. So that's it. Okay. So far I told mostly about structures that you make, take out, and they react. Is there any way that you can establish more stable structures? Then you have to consider why do they react when you take it out? What's the charge of aluminium in your film?
Positive.
Positive. Can we be a bit more specific, quantify it? It is plus 1, 2, or 3, or 4 or 5?
1. 3.
3? Yes, I'll go with 3. So it's plus 3. How many alcohols do you need to react with to saturate it? No, not to saturate, but yes, to saturate in charge-wise.
3.
3. So that means that you get an aluminium with 3 oxidants around. How do you pack 3 oxidants around a metal? It comes in this triangular fashion. So that means that that metal is pretty exposed. We can't shield that metal. It's so exposed, and the aluminium here, it doesn't really enjoy this threefold. The very fine aluminium in nature or elsewhere is either in a tetrahedra or in an octahedra. And if you can put an octahedra around an aluminium, then you're shielded it. So rather than going to alcohols, you could go with the carboxylic acids, because then you have your friend oxygen over here, which is just a coordinating oxygen, but it can shield this in a nice octahedral manner. So by flipping over to carboxylic acids, you should in principle make much more stable materials. And guess what? You do. So we played around with different sort of aromatic type of molecules, this here, and then by doing the aromatic molecules you do get look at the scale here. This is no ounce any longer, it's actually nanometers. So Christoph, when you talked about the nail growth, and this here can actually enhance your possibilities greatly. Now we're up a factor of 10 in growth rates versus normal inorganic growth, and it can scale with a number of carboxylic acids, not necessarily so. You get 4 of them. Here you get 3 of them. It all depends on how they pack and how they occupy the surface that you have. The very most known explored one is this 1,4 version, because you imagine it to grow vertically. Not necessarily so, but it do show, yes, a diminishing growth with increased temperature, but a fairly high growth at a higher temperature. And benzoic acid doesn't grow. So this is more or less as a test to see if you need a biofunctionality. But again, if you now go in with an ozone pulse here, yes, it grows. So you can functionalize that in this one as well to get it into growth. So that's it. Yeah, and you do get very nice saturation. The TMA doesn't spike. And so this, I would say, is one of the beautiful QCM experiments that you can do and characterize. Again, the amount of TMA that you have, the saturation of the aluminium on the surface seems to be more controlled on the surface itself. A common denominator here that you find is that they are flat. This is a roughness of a quarter of a nanometer is sometimes difficult to characterize, but as a typical roughness, unless some features you get here. A low roughness is coherent with an amorphous structure. And the majority of what you're going to make is going to be amorphous. But a low roughness gives you typically very little problems if you want to have a conformal structure as well. Crystals stand out and can form challenges. Like this was here with an aromatic stiff backbone. What happens if you then go with a soft backbone? For the linear dicarboxylic acids, get oxalic acid here as the first one. The growth rate versus temperature looks a bit different. You have some oxalic acid, for instance, which is very stable. If you just want to test functionalities, oxalic acid is a really good go-to version. Very easy to work with, even down to very low temperature. But then as you increase the linearity, then you get this interesting feature here. Drop in temperature, but here you get an increase in temperature up to, this is ridiculous. You're having a growth rate is much larger than the length of the phenolic acid. So clearly there is something that is not controlled here. But still, let's look a bit more into what we find here. Let's not choose the phenolic acid, because that was a bit more difficult to work with. Let's choose, for instance, the glutaric acid, which has this strange shape, and look a bit more into the saturation of that. So for a comparison, these were the curves for the aromatic, and this is then for the linear. Okay. The linear oxalic acid looks beautiful, not spiking in TMA, oxalic acid. The increase in 1 carbon, you do get more spikes from malonic acid up there. TMA looks fairly nice. If you then go for the glutaric, now we're up to 3 additional carbons in between here. The TMA behaves strange. And this is something that we have reproduced and tried to look into. So again, the glutaric acid, that's this one. And if you then just vary the pulse length of the TMA and look at what you get, then 0.5 you don't really get much film. 0.75 you increase the growth. 2 increase the growth. 1 you increase the growth and actually have a fairly nice growth, but then it drops again. So something is then etching it. We will get back to this when we talk about ALQ3 in the end, but you can have a killing effect by overpulsing some of your precursor as well. Not really, then it gives you some warning signs about conformalities, but you can enter into this type. It can be that you then, the strange thing here is that you see this effect when you pulse in the TMA. If it is a killing effect that then double bonds to your surface, you would have anticipated as a function of the amount of glutaric acid, not as a function of TMA, but still. Okay, so those are some effects. The stability of these in water increases with the number of carbon chains, or actually, this is the contact angle as a function of carbon in the chain. For the smaller ones, they dissolve. And metal oxalic acids, they dissolve. So that's not so surprising. You need some amount of carbon in there. Their densities are more or less very similar, even though you vary the number of carbons in the chain. It actually goes a bit more like this. You have this step shape here, which we are uncertain why. It drops with the number of carbon, yes, but it functions like this. None of these are crystalline, though. You can, for instance, increase additional double bonds into the structure and then see what happens. Yes, you then increase the growth rate nicely. You do kill off that huge bump that we had in the beginning. Here we got the aluminium from uric acid, which has become rather popular as a moth material now as well. So that's very easy to grow. Again, amorphous, apart from some incidents that we don't know too much about. When you're working with carboxylic acids, you have a nice feature in the FDI spectrum that you can play with, and that's the feature around here. Because this can tell you a bit of whether you're bonding on your bonding scheme, whether you are having a more or less a bidentate complex, unidentate, or a bridging complex. The splitting of the peaks here can give you some information, and that's kind of nice to follow when you subtreat your material later on. Okay, you can branch them, and again, there are some very consistent appearances with temperature. Okay, so what can happen with your thermal when you expose it to such a surface? That's where we more or less enter the field of multiplex, I would say. Is that what we try to simulate here is what if your precursor enters into the bulk of the film? So this is a precursor, a purging time, and a pulsing of the next precursor, and a purging time. And there is actually a step in growth here. So this thickness here is a bit thicker than that, but not very much. So if you the red layer is a lot of precursor in it, and you get rid of that precursor by diffusing out when the film is thick. No, thin. Sorry, thin. But if you then increase the thickness, then suddenly you don't have enough time to get rid of that precursor in there, so you have some that remains for the next pulse. And that grows more or less like a bulk saturation. So it's a reservoir that is being consumed, and you increase the growth. You can continue with this, and eventually you get a steady state. A steady state where you don't have enough time for all of this to empty, but you have a constant concentration in here, so your growth is going to be constant. Your additional growth is going to be constant. We've seen such effects, particularly when we use lithium as a precursor. That's for the battery material, because lithium is so highly mobile. So it seeps in and out of the film. If you then allow different concentrations in your film and then simulate the QCM signal, then it looks as normal, but you build up spikes at a period before it suddenly takes off. So if your QCM signal behaves something like this, then it might be due to nucleation exists, but it also might be due to the fact that you are absorbing material into the film. Particularly, do then look at how the QCM detail looks later. These are the saturation curves that were simulated, and then you simulate this growth for various temperatures, because you have a higher diffusivity at higher temperature than you have a lower temperature. So if you do it as a functional temperature, you should get a growth rate versus temperature that looks like this for somewhere in here. And this bulb there resembles this bulb here. So we do have a certain growth over here as well, in here. So if the growth rate versus temperature is similar to this, then there is a hint. For growth of trimetal aluminum and glycerol, we have a fairly nice Q7 signal at the beginning, but suddenly you do get spikes. And for this one, you do get actually spikes for both of them. This is the simulation of what the spikes should be if they behave that. Yeah, so this can be. That means, when this happens, that you have a very large growth rate, because you're basically not just surface saturated, you're bulk saturated. And then perhaps you can reach these 4 nanometers per cycle. Okay, you exploit the bulk, you have a tremendous large growth rate. I would say if you get an end product that is worth using, then why actually bother about the fact that you have a ridiculously high growth rate? It's your benefit, not your drawback. It creates the science a bit more hassle, but that's it. Okay, so now we talked about alcohols, we talked about carboxylic acids, we briefly touched on the amines, but is this something that you can exploit? For water and a metal, you do get an oxide. And if you do then use alcohol, you get a metallocone. What do you call it when you use a carboxylic acid? I don't know. You can invent some names. If you're using the amines or other types of functionalities, you can create many different sorts of materials. You can, and by exploiting many metals as well. But what I would like to compare is these. The water with an alcohol with a carboxylic acid. Which of those should be most reactive? And now I'm relying on your organic chemists. Carboxylic acid. Why?
Because the double bond and the 2 oxygens there.
Yeah. And definitely also the pKa, the acidity. pKa is a measure or a accounting on how strong this bond here is. The higher the pKa, the stronger the bond. The lower the pKa, the more likely it wants to just donate that proton. And then the question is, what is pKa in water? It is not 7, it is 14. So that actually means that the protons in water, they are fairly stuck. What we've done there is to then use highly reacting metals to get it to react. But now you can go in and use a highly reactive functionalities here to then get it to react. If you want to grow oxide for these THD type of complexes, you usually use ozone. Water is no good, but you go to ozone. Will these be good? And where is actually the border? So this is something that we have tested. Cobalt, THD and water gives you actually growth, but very little. A growth rate that is ridiculously slow. If you then rather use a hydroquinone, you do increase the growth rate some. It is not fast, but you do increase it some. If you then swap to terephthalic acid, then suddenly you have a much higher growth rate. And you get a much more stable film as well. And you have relatively nice saturation curves that you can measure. Still, you have a reduction in growth rate versus temperature for this particular system, where you got a divalent here and the 2 functionalities there. But in essence, you are depositing more or less the same material throughout. Okay. If you do the same manganese, which is a trivalent, then water is no good. And hydroquinone, you have this interesting fact here. Again, if you overpulse your metal, you lose your film. And this is something that we have verified that will happen. So it is not just an artifact, it's there. But if you then rather swap it with terephthalic acid, you do have a fairly nice growth, similar to the cobalt, but you have a much stable growth with increase of, as a function of temperature for this 3-valent to the divalent THD. So for the divalent carboxylic acid, that's at high temperature. It's still usable, and this is in fact interesting because this manganese THD tends to decompose at 240 degrees, but here we can actually use it exposed to higher temperature. For an oxide, you can't use this above here, for instance. Terbium, likewise, actually grows very nicely, but why would we want to use terbium? Well, because it illuminates. So by using these organic structures with the luminescent lanthanides, you have a very nice absorber, ring structure absorb light, and your lanthanides, they luminance nicely. So this combination there works brilliantly. Okay. So I would say yes, reactivity goes relatively hand in hand with the pKa value. So use that as a guide when you're selecting your chemistry as well. And then the question is, okay, can we make artificial Teflon? Can we make a super nice hydrophobic surface by just adding in a lot of fluoride? Do you know the origin of this here was that we got the Olympic team for skiing, Norwegian team, on visit and wanted us to make a super gliding ski surface by ALD. That's not why Norwegians are good in skiing, because it wasn't turned into practice. But we had discussions. Okay, so the fluorinated compounds, if you compare these here, they can be grown volatile. It's actually easier volatile than the fluorinated structure than just the ordinary hydrogenated structures. A bit more tricky to try to find the QSM temperature that you like to have. 160 degrees you seem to saturate very slowly. 180 degrees you have nice growth. 200 you have basically very little growth. And similar with the glutaric acid as well. Drop in temperature when you increase the temperature. Yes, you do get fairly nice films. They do react on moisture in the air. Okay. So we want to make a hydrophobic material, but when you expose them to moisture, you do get this crystallization here. This crystallization can be, in fact, that your material crystallizes into a metallic frame structure, which is interesting. But here it may be that we have an excess of some or unreactivity of some, but it won't really stable in air. They have a surprisingly layered structure when you look at it from an X-ray diffraction point of view, because all the peaks that we find, the black one here is for pure starting material, the purple one is for the film itself, and they're all multiples of each other. So we would anticipate a structure like this, but those are the only peaks that we get. Can't get any in-plane diffraction, but it's tremendously narrow when you do rocking curve on it. So there is clearly a layered structure here. This film here, we expose to air. And this film here is, yes, it's true, 1.7 micrometers. This grows nicely. So for going into this MLD type of fashion, we are going to be able to discuss with this PVD people again. So, but within 30 minutes, it increased by 200 nanometers. And when you expose it to higher saturations of water, you do get it blisters, you do get some additional features. And but then, what about aluminium? Wasn't it saturated enough? We coated the surface of silicon powder, ran it into a solid state NMR, and got the fact that yes, only all the aluminium was octahedral coordinated, as we saw in the beginning. So we got that. It dissolved in water. So we're going to try to make a hydrophobic material which was easily water soluble. Now I rely on the organic chemistry. Why does this happen? Why did it fail? What happens to the pKa value when you then change your hydrogen to the fluoride? it goes down. So that means that at a certain point of view, yes, you would like to weaken the oxygen to hydrogen bond. But at some point of view, you're also weakening the oxygen to the metal bond. So that's what we anticipate to happen here when we fluorinated it, is that not only did we increase the reactivity, but we also decrease that metal complex itself, the stability of that. Okay. But MLD can also be used for different types of functionalities. One of the go-to stuff that I've tried to is why not try to make a material just purely on hydrogen bonds. That would be super. And with no bioreaction, with no byproducts whatsoever. A stable nitrous material there would be melamine and cyanuric acid, not this one, that's a misspelling, because here you get all hydrogen bonds and can make this really stable hydrogenated material. You have melamine, it evaporates over here, the cyanuric evaporates over here, but melamine cyanurate, okay, it's a fairly close temperature limit that we can work with. So in essence, this didn't work. But they are very nice molecules to play with, and you get this tautomerism between, for the cyanuric acid, where the protons can flip between these states as well. So by playing with this, and we then, rather than letting them react with each other, because it didn't, we added in aluminium or zinc through this highly volatile. Get beautiful QCM signals in principle. You get some spiking of the double zinc, not with the TMA. And so we do produce a very nice material per se. But in essence, but what we saw in effect is that when it took out the films made with aluminium, they reacted with air. If you look at this one, this is the trimetal aluminium with melamine. And we just try to take one and place a droplet of water on it to see what happened. And you get this bubbling, so that it has a really vigorous reaction in here. So obviously you have unreacted something, or you have really highly reacted aluminium in there. So what could it actually be? But whereas the whereas the diethyl zinc version, they were stable in there. You could measure nice contact angles. It didn't happen, so those are actually dead stable. In there. So why this? You can measure the composition with all the materials, and very little hydrogen in the one with the zinc and cyanuric acid. So high reactivity, and zinc and melamine. You had basically you have also very little hydrogen. For the trimetal aluminium, you see that you have a reaction from going through your film itself. So obviously they react. But given so, then you have to consider what is actually trimetal aluminium. Trimetal aluminium is this aluminium with 3 metal groups. Okay, in a precursor when you start, it is actually dimer, but at some point it's converted into a monomer. And as a dimer, it's tetrahedrally coordinated. But this here really would like some electrons. So we could coordinate it into these nitrogens here and make, in principle, a structure. And I think it was Stephen George that showed that you could make this Dubco molecule here, a trimetal aluminium, and you can make a nice stable film until you took it out of the reactor. So these are also highly reactive. That means that you have ligands still intact. And this is something that we see more and more in exploring into different parts of the chemistry, with using, for instance, isopropanol as a ligand type. You do get your fragments still intact in the film sometimes. Sometimes you get a nice, stable, don't really know what, but it's stable, definitely the composition that you anticipated, but it's there. So then we made something with the hydrogen bonds. Can we go further? For instance, if you try to react this with hydroquinone, you get this network structure, bifunctionality. What if all your functionalities is on one part of the molecule? That would then, in principle, produce a molecular structure itself. This molecular structure is interesting for OLED application because it has some luminescent material in OLEDs. Can you play with that? And yes, you do get saturation for pulsing of these. Not the most beautiful. Purging, you can get rid of quite a lot of the material depending on the temperature. So it is an unstable in that point of view. But you have a growth that you can follow and play with. This is for aluminium, this is for zinc, and this is for titanium. And you do make these molecular structures per se. All of them has a drop in growth rate with increasing temperature. It shows you that the material itself is not super rigid, but it's a molecular entity. Fairly low roughness. Anticipate that you get a trimetal aluminium, that you get a reaction going on with that, and you have a part reaction that you then restructure it when you get a new precursor in. Okay, that's it. But if you go in and look carefully at the growth itself, you find that for longer pulse times of trimetal aluminium, it spikes. Strange. You can actually lose film. So this is a pulse of the your 8-hydroxyquinoline, trimetal aluminium, okay, but still not too much of it. You build film, and then we just went in and shooted quite a lot of trimetal aluminium, and we lost everything. So by overpulsing the metal again, you can etch the film. It happens that we found a work from the 60s that actually shows another stoichiometry between aluminium and the 8-hydroxyquinoline, which is more volatile. So in here case, when you change the composition during growth, you lose film. And this may also cohere to what we saw from some of the strange growth rates later on and overpulsing of the metals. The ALQ3 has been claimed to be reactive towards water. We try to expose it and it's no mass change. But what you can say is that it recrystallizes into another crystalline structure. That it does, and that affects the luminescence. But these luminesce fairly nicely as well. So it's a nice system to play with for teasing up different sort of excitation and luminescence. Yes, I think we've covered some of these reactivities. Alcohols, they're volatile, so they're nice starting points as a precursor. They are reactive enough, more reactive than water, but the end product is typically not stable in here. It might be. Depends on how you shield it and what type of metal you're using. Carboxylic acids are less volatile, but they are much more reactive, produce water stable and air stable product, provided that you have a large enough organic structure. You are perhaps building a porous material, and that can function as a sponge. That can give you a tremendously high growth rate. If it gives you the product that you're after, exploit it. In the reactivity, I tend to look for the pKa's, but you can be fooled as well because you can actually weaken what you make. The hydrogen bonds, well, I have not yet found a structure that works only by hydrogen bonds, but also van der Waals structures can be used, but again, higher temperature typically kills your material. And for this, I'm very grateful for you who are going to continue this work. In that sense. So with that, thanks. Questions, discussions? Ideas, fright?
Excellent for the very... yeah, sorry. So lots of the studies were conducted with TMA. Lots of the studies were conducted with TMA as the metal source. And I wonder, as we have heard lots of issues where we have infiltration of this precursor into the, well, emerging hybrid system. By chance, did you have any opportunity to test other aluminium precursors? I mean, more bulky ones that might not infiltrate into the ozone.
We have not tested other aluminium precursors,
Okay.
but we have tested the different types of titanium precursors, zirconium precursors, these cobalt, all rare earth elements and things like that, and I would say we tend to like these large, bulky THC type of molecules because here you can actually work with them. Even though they have low reactivity, because we exploit the carboxylic acid functionality in that sense. But I guess where we're going is that go large with the molecule so that it doesn't go into pore. And how large a molecule would then need to be, I don't know. But I'm really interested to get your feedback on that. I guess it would go hand in hand with the rest of the structure as well. And there are things that I haven't talked about here, but we're going to cover it later. You can go in with helping molecules during growth as well. So there are possibilities not to do ABC, but growth, but actually get in with an aid that doesn't stick into film later on, but it can affect growth. This is definitely what we saw when we grew, for instance, the UIO66 structures. Then we needed acetic acid during growth to get where we wanted, because otherwise we had an excess of the terephthalic acid in the structure. Sometimes you don't need it because the molecules take care of that themselves. But it's this conflict that you like, if you want to make a porous material, the porosity is going to be there and perhaps kick you in the leg, or perhaps aid you. This is definitely something you saw with the lithium material, because if you want to make a lithium conducting material, and you're very annoyed by the fact that the lithium is conductive during growth. So it's this conflict of interest with that you would rather just have to exploit. I guess that Rob Unler is going to talk later on his approach, where he just starts to make the oxide as pure oxide and then goes into the layer to convert it into hybrid material, because that's also an approach. So there's not one way to roll here.
Let's thank for lunch.